Ladies and gentlemen, it's my great honor to give my presentation. My topic is a 128 multiply 1 pixels high dynamic range SPAD image sensor in 0.18 micrometer CMOS technology. My name is Cheng from Nanjing University, China. Here is my contents, including introduction, system design, experiment results, and conclusion. As we know, CCD and CMOS image sensors translate incident photos to charges and store them in a well. The left picture is the CCD structure, and the right one is the CMOS structure. The depression layer, which is highlighted in the red block, is a well, and they store the charges. The dynamic range of CCD and CMOS is equal to 20 log V maximum divided by V minimum. However, the V maximum is limited by 4 well. So generally, CCD and CMOS dynamic range is about 65 to 75 dB. The SPAD, which is short for single photon average diode, detects photon incident intensity by counting photon event directly. When a photon inserts into the SPAD, it may cause an avalanche and output a pulse after the quenching circuit. So that means one photon may cause one pulse. So if we count the pulse numbers in a certain exposure time, we can record the optical information of an object. Based on this theory, we design a SPAD chip. The SPAD device is a P plus N well junction. The performance of the device is as follows, including pixel size, fill factor, photon detected efficient, dark count rate, and data time. Here is the ideal light response curve. It is limited by 2 items. The lower one is the dark count rate, and the higher one is the 4 well. Because the data time is 20 nanoseconds, so the 4 well is 1 divided by data time equals 50 million counts per second. So the ideal dynamic range is up to 94 dB. Here is the chip structure. On one side, this is the SPAD pixels, and the other side is system circuits. For more detail, for more information, let's see the system diagram of the SPAD image chip. From up to down, here is 128 SPAD pixels with quench circuits respectively. When the intake signal is on, the readout circuit read the SPAD pulses and shape them and transmit to the 15-bit counters. And when the intake signal is off, the counter stop counting the pulses, and by the trans signal, the counters transfer the data to the latches. At this moment, the above circuits can be reset and for the next working period. And at the same time, the address selector selects the latches to output the data to the IOs. Here is the logic control of the chip system. This is the SPAD camera. The chip is inside the box, and here is the lens. For one working period, the SPAD pixels focus on a line of field, and detect and output one data for one working period. Then the SPAD is rotating by the platform, and the line of field pushes forward one by one, and then output the image whose size is 128 multiply n for n working periods. Here is the experiment result. This is a photo of the standard dynamic range test card, and the brightest part is 19,013. The darkest part is 2. So the dynamic range is 79.6 dB. However, the ideal maximum value is 100,000 because the exposure time is 2 milliseconds. So we carried out another experiment. Here the outside is the brightest part and is 30 milliwatts per square centimeter, and the darkest part is inside 1 microwatt per square centimeter. So the dynamic range is 89.5 dB. The picture A, we can see that the outside is clear, but the inside is undistinguished. It is a high 8-bit image display, and the picture B is a low 8-bit image display. We can see that the inside is clear, however, the outside is overexposed. But our SPAD camera do record the high dynamic range information. So we use the log image display, and from picture C we can see both the inside and outside is clear. Here is the conclusion. A SPAD chip with 128 multiply 1 pixels in 0.18 micrometer CMOS process is implemented. SPAD camera can achieve 89 dB high dynamic range, which is 20 dB higher than CCD and CMOS image sensors. And low dark count rate SPAD device can widen dynamic range further in the future study. Thank you.